Welcome to lecture 38. We're going to introduce in today's lecture the Hubbard model. We're going to talk a bit about how one understands how the Hubbard model works, and we're also going to discuss some of the symmetries of the Hubbard model which allow working with solving the Hubbard model quite a bit easier. So the original Hubbard model starts off with a picture from Neville Mott, who asked the question, what would happen if I had a collection of hydrogen atoms? And I brought those atoms closer and closer together. Now, when they're isolated hydrogen atoms, they each have one electron. We're going to ignore the fact that they might try to find another hydrogen and bond into a hydrogen molecule. Let's assume for the moment that that doesn't happen. Those electrons are really bound to the hydrogen atoms. So initially, when the collection of hydrogen atoms is very far apart, those electrons are bound to the atom, and I cannot pass electrical current through my collection of hydrogen atoms. Now, when I bring them closer and closer together, eventually those 1s wave functions will start to overlap, and it'll eventually become a band structure corresponding to having the hydrogen atoms on some solid lattice, which will have overlap, and we know that that will give a band structure from your solid state physics class. And then there's an energy band, and with only one electron per latticite, that's a really nice metal. So there's a transition from the insulating phase when the atoms are far apart and the metallic phase when the atoms are close together, and that's not described by simple band structure theory. And this is something that is called the Mott transition, and the model that is one of the best models to use to describe this transition is something called the Hubbard model, which we're going to get into in more detail in just a moment. So let's first talk about how we describe the tight binding model of those 1s electrons. When we do it in the second quantized formalism, we can think of this as the electrons can move between one of their nearest neighbors when the hydrogen atoms are close enough to each other. We'll call that hopping integral minus t, and then we would have a sum over all nearest neighbor pairs I and j, and a sum over spin of this operator c dagger I sigma c j sigma plus c dagger j sigma c I sigma. You see what that operator does is it removes an electron at site j with spin sigma and replaces it with an electron at site I with spin sigma. You can think of that as hopping the electron from site j to site I. And then the other term is the Hermitian conjugate. It does the opposite. It removes an electron from site I and moves it to site j. This angle bracket ij denotes nearest neighbor pairs, and we only count when we do the sum through each nearest neighbor pair once. So if I have nearest neighbor pairs 1 and 2, 1 and 2 appears in the sum, but 2, 1 does not, because that would be counting that nearest neighbor pair twice. Now, because the electrons are negatively charged, we also expect them to repel each other, but because the electrons are mobile, our understanding in a solid is that that repulsion is really localized to when the two electrons are on the same lattice site, because when they're on different lattice sites, the electrons can rearrange themselves in such a way to screen the Coulomb interaction. So the simplest approximation is to simply say that they repel each other only when they sit on the same site. That operator that we call U hat is given by whatever the strength of that repulsion is that we call U, multiplied by a sum over I of Ni up, Ni down. You can see that operator Ni up, Ni down is equal to 0 unless I have two electrons at site I. So if I have no electrons at site I, or just one spin up or just one spin down electron at site I, that product of number operators will equal 0. But when I have both a spin up and a spin down at site I, that product will equal 1. So to make the Hubbard model, we actually add together both of these terms, and that is described by this Hamiltonian. H Hubbard is equal to minus t, the sum over nearest neighbor pairs ij, sum over sigma, c dagger I sigma c j sigma plus c dagger j sigma c I sigma, plus u, sum over I, Ni up, Ni down. Now we can illustrate what this looks like on a lattice by thinking about having electrons, which I'm indicating at those lattice sites, which are where these lines cross, as either up arrows or down arrows. And the hopping will take an up arrow from a site that is occupied with an electron to a nearest neighbor site. In this case, if it's on a square lattice, the hopping will either be in the vertical direction or the horizontal direction. And when two electrons are on the same site, we get a U that is given by the Coulomb repulsion. So electrons can hop on nearest neighbor sites as long as there isn't an electron on that nearest neighbor site that has the same spin. If there is, then the electron cannot hop between those sites. And so you can really just think of this model as moving little checker pieces on a checkerboard lattice, moving them from one square to another square. The centers of the squares are forming the lattice, and the red checkers or the black checkers are representing spin up and spin down. And when I have a red and a black on the same site, then I have a U interaction, and I can never have a situation where I have two blacks or two reds on the same site. And so if you want to get concrete about what the Hubbard model is doing, that's essentially what it is doing. And then the only thing I have to keep in mind is that the wave function that describes this has to be completely antisymmetric, but we know if we use the second quantization formalism, that's guaranteed. We can transform the model into momentum space, and if we look in momentum space, that means we're looking in block or plane wave bases. Then we would describe new operators that we're going to call A dagger K sigma. K here is a momentum label, and we're going to write that as 1 over the square root of the volume, where V is the number of lattice sites, sum over J e to the I K dot Rj, C dagger J sigma, and then AK sigma is the Hermitian conjugate, 1 over square root of V sum over J e to the minus I K dot Rj, Cj sigma. Then Cj dagger sigma will equal 1 over square root of V sum over K e to the minus I K dot R J A dagger K sigma, and Cj sigma will equal 1 over square root of V sum over K e to the I K dot Rj A K sigma. Now that we've determined how the C dagger J sigmas and the Cj sigmas are determined in terms of these A dagger K sigmas, we can substitute into the Hamiltonian, and so the Hamiltonian H is minus T sum over nearest neighbor pairs Ij sigma, 1 over V because I have 1 over square root of V's, sum over K and K prime, e to the minus I K dot Ri plus I K prime dot Rj, A dagger K sigma, A K prime sigma plus the Hermitian conjugate of that, which is e to the I K dot Ri minus I K prime dot Rj, A dagger K prime sigma, A K sigma. And then the interaction term is plus U sum over I 1 over V squared, sum over K1, K2, K3, K4, e to the minus I K1 minus K2 dot Ri minus I K3 minus K4 dot Ri. The I index is the same for both of those terms. A dagger K1 up, AK2 up, A dagger K3 down, AK4 down. Now note, for nearest neighbor pairs, that term Rj can be written as Ri plus delta, where delta is the nearest neighbor translation vector. So I'm going to be substituting that in, and you can see then every Rj will get replaced by an Ri plus delta, and I'll have a sum over delta that will then take into account the sum over nearest neighbor pairs Ij. So we're going to substitute that in. What we're going to see is that 1 over V sum over Ij e to the minus Ik dot Ri plus Ik prime dot Rj is equal to 1 over V times a half the sum over I sum over delta e to the minus I K minus K prime dot Ri plus Ik prime dot delta. The 1/2 is coming from the fact that we're only counting those pairs once, but when I sum over I and delta, I'm actually going over each of those pairs twice. And that will give a 1/2 sum over delta e to the I K dot delta delta KK prime. And that object that is multiplying the sum over delta, you can see that's actually a sum over cosines. And that's going to actually end up being related to the band structure. So the first term, the kinetic energy, can be written as a sum over K and sigma, epsilon K, A dagger K sigma, AK sigma, with epsilon K equal to minus T times a half times the sum over delta, e to the Ik dot delta plus e to the minus Ik dot delta, and that is given by minus T the sum over delta cosine K dot delta. Okay, now the second term has a lot more terms in it. We get U over V sum over KK prime and Q. That's because it only had a single Ri in it. Let me go back to that term. it only had a single Ri in it, so when we do the summation, I'm going to get K1 minus K2 plus K3 minus K4 must equal 0. So I can replace K4 by K1 minus K2 plus K3, and we find it's easier to do it in the way that it's written here. We can write it as U over V, the sum over KK prime Q, A dagger K plus Q up, AK up, A dagger K prime minus Q down, AK prime down. I encourage you to pause the video and make sure you can properly get that representation of the Hamiltonian in momentum space. And now when we put them both together in momentum space, we get sum over K sigma epsilon K, A dagger K sigma, AK sigma plus U over V, sum over KK prime Q, A dagger K plus Q up, AK up, A dagger K prime minus Q down, AK prime down. And you see in this case, the hopping term is now diagonal, but the interaction term becomes off diagonal because it involves a coupling between different K vectors. So in real space, the Hubbard Hamiltonian had the first term, the kinetic energy, being complicated and not diagonal, while the interaction was nice and diagonal, whereas if I go to momentum space, the opposite is occurring. The hopping becomes simple and diagonal, but the interaction term is not diagonal. So there's no simple way to find a representation where I can easily diagonalize the Hamiltonian, and that means the key problem is to find the eigenvalues and properties of the ground state for arbitrary values of U, and this is a hard problem. It becomes very hard because the Hilbert space that corresponds to having V electrons grows as 4 raised to the V power. And V doesn't have to get very large. The biggest supercomputers in the world can handle maybe a V on the order of about 24, 26, something like that. And remember, in a solid, V is on the order of Avogadro's number. So you can see that the size of this Hilbert space, even though it's finite, gets very, very large. So in order to have some better understanding of what's happening with the Hubbard model, we're going to study some of the symmetries. And the first thing is to look at what happens in the case where the lattice is a bipartite lattice. So a bipartite lattice means I can separate the lattice into two sublattices. Again, you can think about the checkerboard with the red squares and the black squares. And we have a hopping only between opposite sublattices. So if I had nearest neighbor hopping on a checkerboard lattice, if I'm on a red square, all of the nearest neighbors, which are horizontal or vertical neighbors of that site, are opposite colors. They're all black. And so the hopping goes from red to black, or if I'm on a black square, it goes from black to red. And whenever you have an ability to separate into those two pieces where you're always going black to red or red to black, that's called a bipartite lattice. I never hop along a diagonal, which would be red to red or black to black. And examples with nearest neighbor hopping of bipartite lattices include the simple cubic lattice, the square lattice, which we just talked about with the checkerboard, the body-centered cubic lattice, but it does not include the face-centered cubic lattice or the triangular lattice. But in the case where I have a bipartite lattice, then there's a symmetry which says if I take the hopping and I change the sign of the hopping, that doesn't change any of the energy eigenvalues. So that's a symmetry of the system. So let me now prove that for you. We're going to define two new operators that we're going to call C prime dagger I sigma, which is going to be minus 1 raised to a power that I'm going to call epsilon of I times C dagger I sigma, and C prime I sigma, which is minus 1 raised to that epsilon of I C I sigma. The epsilon I just takes two values. It's 1 if I lies on an A sublattice, so again, think about red squares, and 0 if I is on the B lattice, again, think about black squares. Then in that case, you can see n prime, which is a C dagger I sigma, a C I sigma. That'll have an epsilon to the a minus 1 raised to the 2 epsilon I. But 2 epsilon I is either 0 or 2, and minus 1 to the 0 or 2 is always equal to 1. So the U term in the Hamiltonian is unchanged because the Ni primes are exactly the same as the Ni's. On the other hand, if I look at the Hamiltonian for the hopping, every time I have a C dagger I sigma with a C J sigma, because the I and J's are on different sublattices, I always will have a factor of minus 1 raised to the epsilon A sublattice plus epsilon B sublattice. Please be sure you understand that. Always one of those factors corresponds to a red square and one to a black square because it's a bipartite lattice. And that means I have minus 1 raised to epsilon of A plus epsilon of B, but that's always equal to 1. And that means I'm going to change the sign. So the hopping is going to change from minus t to plus t, as shown in what's written out for the Hamiltonian. Just note that there's a prime that got dropped off of that last Cj sigma in the hopping term. So since C dagger I sigma Cj sigma is equal to minus C dagger I prime sigma Cj prime sigma when I and j are on the different sublattices, that's the reason why that holds. And what that tells you, because this is a unitary transformation, none of the eigenvalues have changed. The eigenstates may change, but the eigenvalues have not changed. And that means the set of eigenvalues is symmetric with respect to t goes to minus t. Now, the next symmetry that we're going to talk about is something called a partial particle hole symmetry. And for this, what we have is we're going to define new operators called d dagger I up. It's equal to ci up times minus 1 to that epsilon to the I. And di up is equal to c dagger I up times minus 1 to the epsilon of I. You see what I'm doing here is I'm interchanging the creation and annihilation operators for the up spins. But if we look for the down spins, d dagger I down is c dagger I down, and di down is ci down. So I'm not changing holes with particles or interchanging creation with annihilation operators for the down particles. Because these objects obey anti-commutation relations, this does not change the anti-commutation relations of the C and C daggers with each other. Okay, so what we find now is if I look at C dagger I up, Cj up plus C dagger J up, Ci up, that becomes D dagger I up, Dj up plus D dagger J up, Di up. How does that occur? Well, for the up spins, the Ci up becomes Di up, and the Cj up becomes a D dagger J up. I have to interchange the order of those two, which would give me a minus sign, but I also get another minus sign because there's a minus 1 raised to the epsilon of I plus epsilon of j, and so those two minus signs are going to cancel, and that gives me that term, the sum over both of those terms, is preserved under this transformation. Now the n operator, ni up goes to di up, di dagger up. The minus 1 to the epsilon terms cancel, and I can rewrite that as minus d dagger I up, di up plus 1. So that tells me n up, when I sum over the entire lattice, will go to v, the number of lattice sites, minus n down. And so the Hamiltonian is preserved in the sense that the hopping term is preserved, but if I look at the u term, it's going to change sign. It's going to be a minus u times a d dagger I up, di up, d dagger I down, di down. That's because the down spin operators are unchanged by this transformation. And then there's an extra term that's coming from that 1 that's going to give me a plus u sum over I, d dagger I down, di down. So now if I look at the energy as a function of u, n up, and n down, because the total eigenvalues are unchanged, that is going to equal the energy for a minus u with v minus n up and n down, plus this shift which is given by u, n down. Okay? Again, be sure you understand that. What we're simply saying is that the eigenvalues of the original Hamiltonian, which is just some set given by u, n up, and n down, will be exactly the same as the eigenvalues of the transformed Hamiltonian, which corresponds to minus u, v minus n up, n down, plus this extra term, which involves u, n down. Okay? Now, in the case where n up is equal to n down, then, and they're both equal to v over 2, that's the case that's called half filling, then what we find is E of the positive energy, u v over 2, v over 2, is equal to E of minus u, v over 2, v over 2, plus this shift, u, v over 2. And then up to a constant, the energies will be symmetric as u goes to minus u at half filling. There's an overall shift of a constant, but other than that, all excitation energies are exactly the same when I undergo this symmetry transformation. Again, please be sure you understand exactly what that means. Okay, now let's talk about spin. Here I'm going to look at the commutation relation of H with the total number operator. Here this K is a spatial index, not momentum. I'm using K to index the spatial indices, so I have I, J, and K are all spatial indices. We're going to look at the commutator then of minus T, the sum over the nearest neighbor pairs, sigma, times C dagger I sigma Cj sigma plus C dagger J sigma Ci sigma with Nk sigma prime. And since Nk sigma commutator with Nk prime, sigma prime is equal to 0, I don't have to worry about the commutation with the U term. And so I have to carefully work out what that is. What we're doing now is we're using the fact that the commutator of Nk sigma with a C dagger or with a C is going to give plus or minus that C dagger or C, depending upon whether it's a C dagger or a C. And it will require the K index to be the same as the I index or the J index. So I'll get a delta IK where it's a minus C dagger I sigma prime Cj sigma prime plus a C dagger J sigma prime Ci sigma prime. And then it'll be plus a delta JK. That's when the K index is equal to the J index, C dagger I sigma prime Cj sigma prime minus C dagger J sigma prime Ci sigma prime. Again, I encourage you to carefully write this down and make sure that using this Leibniz product rule, you can verify that this is exactly what the commutation relation is. I'm just using the commutation relation of an NK with a C dagger or with a C, but you have to recognize that the C or C dagger is on the left-hand side, so that's giving some additional minus signs when we do this. And now we have to evaluate that summation. Using the sum over K first, we recognize that the delta IK and the delta JK will both disappear because there's no K in the terms in the parentheses. And then what we're left with are terms that will cancel pairwise. So you can see the minus C dagger I sigma Cj sigma prime has a C dagger I sigma prime Cj sigma prime right below it. Those two cancel. And then the other two terms will also cancel. And so after that cancellation, what we will find is the total summation, even after summing over all the pairs, is just equal to 0 because all the terms vanish now. Now this only occurs because we sum the total number operator over all lattice sites. If I were to do this just with a single NK, that's not a conserved quantity. And what that tells you is something that you obviously know. As I'm moving the electrons around, they can move from one site to another site on the lattice, but the Hamiltonian doesn't allow me to create or destroy electrons. And that's why the total number of electrons is conserved. Now, because we can work that out for either spin, that means that the SZ operator, which is given by 1/2 the sum over I, Ni up minus Ni down, and the total number operator, which is the sum over N, sum over I, Ni up plus Ni down, they both commute with the Hamiltonian because we worked with just the total number operator for either one of those spins. And anything that commutes with the Hamiltonian will provide a good quantum number, so we can get simultaneous eigenstates that have definite SZ and definite particle number. And again, that's because the Hamiltonian does not create or destroy particles, and it also does not flip the spins of the electrons. Whenever I'm hopping, a red checker goes to a red checker when it hops. It never changes to a black checker. So if SZ is conserved, we can naturally ask the question, well, what about the raising and lowering operators? So you can write the raising operator as sum over K, C dagger K up, CK down. You see what that's doing is it's taking an electron that is spin down at site K and replacing it with a spin up at site K. I hope you can convince yourself that if we sum that over all lattice sites, that corresponds to a total S plus. So we now have to do the commutation relation, and we have the two terms we have to work out, the one from the hopping and the one from the interaction term. The one from the hopping, we have to work out all of those terms. It's the same procedure as what we did before. You have to just carefully work out all of them. We get a delta IK, C dagger J up, Ci down, minus C dagger I up, Cj down, plus delta JK, C dagger I up, Cj down, minus C dagger J up, Ci down. And now when we sum that over K to get rid of the delta functions and sum over the nearest neighbor pairs I and J, again, you can see the diagonal terms between the two lines, they both cancel, and I'm going to get 0 when I sum that up. Similarly, if we look at this product of ni up, ni down, that will commute for each I it commutes, and that's something that's easy to understand. When I have a spin up and a spin down on the same lattice site, the only way I can do that is with a singlet state. And of course, a singlet state cannot have its spin raised. You can also just go through the algebra as is shown for you here. I'm not going to read it out for you. It's a fairly simple calculation, just like what we've done before, and you can verify that that is equal to 0 for each I. So when I sum over I, it still remains 0. Okay, so what we've shown is the commutator of H with S plus is 0. Now I don't have to redo the calculation for H with S minus. I just take the Hermitian conjugate of that equality, and I find immediately that H with S minus is also equal to 0. So that means that S plus, S minus, and SZ all commute with a Hamiltonian, and now that means I can use S squared along with SZ as good quantum numbers. So I can label my states by total angular momentum S and Z component of angular momentum MS. Now there's another operator that also commutes with a Hamiltonian. It does in the case where I have a bipartite lattice, and it's something that I'm sure you've never seen before. It's called pseudospin. We let the J component of pseudospin be equal to Jz is 1/2 that total n operator minus the total number of sites. I hope you can convince yourself, because the total number operator goes from 0 to 2v, that if I subtract v, that total number operator will go now and multiply by 1/2. It goes from minus v over 2 to plus v over 2. So it's kind of looking like the z component of a spin if that total spin was equal to v over 2. We similarly define J plus and J minus operators in the following way. A C dagger I up, C dagger I down times a minus 1 to the epsilon of I, that's summed over all I. And the J minus is the Hermitian conjugate. I have to change the order of those terms, so it's a Ci down, Ci up minus 1 to the epsilon of I. And that first one is a pair creation operator. It creates a pair of electrons, so it's changing the number of electrons. And there's also a pair destruction operator, which is the J minus, again, changing the total number of electrons. So now if we commute the hopping term with the J plus, I'm not going to read out all of those terms. You should pause the video, and I'm not going to cover it so you can't see it, but you should pause the video and go step by step through that and verify that you get that that result is equal to 0. It is using the fact that minus 1 to the epsilon of I is equal to minus 1 to the epsilon of J if I and J are nearest neighbor pairs. And that's because for nearest neighbor pairs, epsilon of I plus epsilon of J is always equal to 1. So you should carefully verify that identity, and then you need to use that to show that this commutator of the pair creation operator commutes with the hopping term. Now, when we look at it with the J term, with the U term, you can see that it's highly unlikely that that's going to commute. The U term is counting the number of double occupancies and multiplying it by U, and the pair creation term creates an additional double occupancy. So if it creates an additional double occupancy, I'm going to increase the number of double occupancies I have, so it shouldn't commute with it. And indeed, when we run through this commutation relation, we find it's given by U times J plus. So that tells me that this is not an exact symmetry of the Hamiltonian. If I take the Hermitian conjugate of that, I will get that the commutator of U with J minus is minus U times J minus. But think carefully about that. Now, go back and think about the simple harmonic oscillator. If I looked at the commutator of H with an A dagger, I got H bar omega times the A dagger. And that was exactly what was needed to show that it was a raising operator, and the A dagger raised the energy by H bar omega. Similarly here, when I hit a state with a J plus, it changes the total number of electrons, but it only changes the energy by increasing it by U. And so J plus is a raising operator for this Hamiltonian H. Now, this doesn't mean that I can automatically get every state just from the vacuum state as I do with a simple harmonic oscillator, because this is a raising operator for a SU2 multiplet. I'm going to explain to you in just a second why this is an SU2 multiplet. but it means that I can only look at all of the states in a given multiplet, and that multiplet can either include all half-odd integer spins up to some maximum value given by v over 2, or all even integer spins from 0 up to the maximum value given by v over 2. Now, to verify that it's an SU2 operator, we have to look at the commutation relations between the jz and the j plus minus. And you're going to have a homework problem that's going to have you verify that the commutator of jz with j plus minus is equal to plus or minus j plus minus, and the commutator of j plus with j minus is equal to 2jz. If you compare that with the commutation relations of sz with s plus minus and s plus with s minus, you see that those are the exact same commutation relations of an SU2 algebra. And if you remember, we constructed all of the states of our SU2 algebra, our LM states, were constructed solely from these commutation relations. And that means that I can think of J as an angular momentum operator just like S is an angular momentum operator. So this Hubbard model on a bipartite lattice has two SU2 symmetries, one which is the conventional spin symmetry and one which is the pseudospin symmetry. Now the raising operator aspect tells us that the energy of a pseudospin mj is given by the energy of the minimal pseudospin for that multiplet, which is given by minus j, plus mj plus whatever the total j is multiplied by u. And again, you're going to examine this on the homework, and you're also going to see how we apply this in the next lecture. Now in this case, when I'm talking about pseudospin, m sub j governs the number of particles because it was 1/2 the total number of electrons minus the total number of lattice sites. So as mj increases by 1, the number of particles increases by 2, and that's why we're going to have a separation into the even or integer values of j and the half-odd integer values of j. So there's sort of two different cases. If I have an even number of particles, I'm running through integer values of j, and if I have an odd number of particles, I'm running over half-odd integer values of j. And in each case, the J plus is going to add a pair of electrons. We're going to end by looking at what happens when we look at the limits u goes to 0 and u goes to infinity. So when u goes to 0, we're going to use the momentum space representation and the bathtub principle. And indeed, that's what you studied in solid state physics when you looked at band structures and how you fill in band structures and you have degenerate Fermi gases and so forth. We just fill in those lowest interacting levels and it will always look like a metal unless I've completely filled the entire band, which would correspond to having twice the number of lattice sites, number of electrons. U goes to infinity, we tend to use a real space representation. It tells us that we're going to have no double occupancies because a double occupancy costs me an infinite amount of energy. And then if I'm at half filling with a single electron per site, because I can never have double occupancies, those single electrons are frozen in place. I don't know whether each lattice site has a spin up or a spin down on it, but those electrons cannot hop because in order to hop, I would create an empty site and a doubly occupied site, but I can never have doubly occupied sites, so I cannot hop the electrons. So the electrons are frozen on each site, and that is an insulator. That insulator is called a Mott insulator. It's an insulator that only occurs because of strong correlations or strong interactions given by the infinite value of u. Now, in the limit of one dimension, the critical u for that metal insulator transition is u equals 0. The instant u is larger than 0, no matter how much larger, I immediately go from a metal to an insulator. And the solution is given by what's called the Lieb-Wu beta ansatz solution, which by construction proved this result. Another limit where we have an exact result is in the limit d goes to infinity. And in that case, the critical u is on the order of the bandwidth. And it is expected in the community that for d greater than or equal to 2, that this u critical will be on the order of the bandwidth. But there is no explicit proof of this. There's only numerical evidence that indicates that this is likely the case. But we don't know for sure because there is no exact solution of the Hubbard model in 2 or 3 spatial dimensions. And with that, we've reached the end of this lecture. In the next lecture, we're going to use these different symmetries and the different properties of the Hubbard model to solve explicitly and analytically for all of the eigenfunctions and energies of the Hubbard model when I have just two sites. So when V is equal to 2, we're able to solve exactly for all of the states and all of the energy levels, and that's what we're going to do in the next lecture.